Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on Building Energy Systems and Auditing. We are in the module number 3. Today is the last lecture on the module number 3, lecture number 15. So, in the previous two lectures, we have discussed about the periodic heat flow, and based on the periodic the temperature changes, outdoor temperature changes and the solar radiation changes, the heat gain through the envelope. In this lecture, we will go to the little bit of details of periodic the heat flow, thermal time constant and the computation or the estimation of the heat flow, that periodic heat flow. So, periodic heat flow we have initially discussed in the first module, the second the lecture of the first module, where we have seen that the outdoor temperature is time variant, and also we have taken that particular time variant outdoor temperature in the last two lectures to compute the total heat gain through the building envelope. So, again if I repeat a bit, the outdoor temperature and the indoor temperature variation will be similar in kind, but there will be two distinct differences. That distinct differences are, if I see a particular periodic profile of 24 hours profile of outdoor temperature and the indoor temperature, I have shown this in this particular graph. The black color curve is outdoor temperature and the red color one is the indoor temperature. So, in that two temperatures are alike, but there is a difference is that the number one difference is there is a phase lag or a time lag. The peak in the outdoor temperature and the peak in the indoor temperature, there will be a delay. So, this is one of the phase shift we will see. We will see that how much time lag or how much delay is going to happen, and that particular time delay or time lag, how it will be imported in the computation of the heat gain through the building. The second distinct changes what we study in this particular graph is that the difference in the amplitude, the peak amplitude. The outdoor max and the indoor max are not same, they are different. So, there is a damping, there is a kind of a damping is happening, because the wall element or the roof element or maybe any fenestration element has some capacity to absorb some kind of a heat, and that heat absorption will actually lead to a kind of the change of temperature in the outdoor and indoor. And this particular phenomena is called discriminant factor. We have discussed this thing in the very first or second lecture already, but we will take this particular two things, the time lag and the discriminant factor, today's lecture for computation of the periodic heat gain through envelope. That is why I am little bit discussing this again, 3-4 slides we will be repeating from the second lecture or so. So, the discriminant factor is the ratio between the indoor max temperature divided by the outdoor max temperature. So, definitely this ratio, this mu ratio will be less than 1, because we can say that from our experience or our understanding that indoor temperature max will be always less than the outdoor temperature max. And how much is this difference? What will be the delta? What will be this delta? Delta will be depend upon the lot of factor. The one of the factor is the density, one of the factor is the specific heat of the material of this envelope also. So, how much it can absorb the heat. That means, if I say the density and also the of course, the thickness, because if the thickness is higher, so it has to actually pass lot of layers one after another layer, and it will take some time to get into in the indoor environment. So, there is a time lag, and also if there is many number of layers, thickness is high, each layer will actually going to absorb lot of heat, and that is why there will be a differential amount of the T max and the indoor max and the outdoor max. So, as and when we can see this mu is less, very less, that means it has a higher amount of damping capacity. So, it will be better for our application in the building. So, we will target if there is the high time lag and also the low mu value. So, if what is the impact of this thermal mass that which actually going to govern this time lag and this particular the discriminant factor. Suppose this is the profile of the outdoor temperature. With this profile, if I say the indoor temperature is something like this dotted line. So, that means this is having a smaller amount of time lag. So, time lag is small, and discriminant factor is also little high, because they are almost the amplitude are almost time lag is also less, and this is also the discriminant factor is high. So, I can say that from the logic that it has a low thermal mass. So, that means it is a kind of a material which may be thin thickness, the envelope is thin, maybe a glass piece of 6 mm glass or 10 mm glass, or maybe it is a material which can conduct heat very fast, it cannot store the heat. So, something like that combination may be there for this kind of the phase difference and the amplitude difference. Whereas, if some other room, some other space is having some other kind of wall in the sense maybe the same material with high thickness, or maybe the same thickness with the high thermal mass material also, then we will see that the indoor temperature will be much lower, the peak is much lower, and there is a phase difference. So, there is a time required to the movement or the conductance of the heat from the outside to inside will take time, number 1, and number 2, the amplitude in the outdoor and the amplitude in the indoor will be much less. If you compare, that will be much less. So, here you see the discriminant factor will be low, it will be very close to 1 or something like that, and there is a time lag is more. So, these two phenomena, the based on the thermal mass and based on the thermal mass and based on the overall thickness and the composition of the envelope materials and all, there will be certain change in the this phenomena of the indoor temperature or the heat the gain inside a building. So, today we will see that how this particular the phenomena of time lag and the discriminant factor will take care in our heat load computation. So, next we will see some of the parameters of this thing, the wall thicknesses and all. So, if I see it is a time lag, as and when the thickness increases, definitely time lag will be also going to be increased, because it will take more time to actually penetrate the high thickness one. So, it is the left hand side graph is actually showing it is kind of a straight line, positive straight line, thickness increases, wall thickness increases, roof thickness increases, and we see the time lag is increases. So, we see our traditional buildings are much of that kind of a nature, probably that is because of we go for the load bearing kind of a structure. So, the ground floor, first floor, those areas, the room sizes are the wall sizes are the high, and also it will going to give you the high kind of a time lag. The second graph, I mean to say this, the left hand side right hand side graph are taken from this Introduction to Architectural Science book, and you see it is the same pattern. The thicknesses increases in the x axis, the time lag increases in the y axis. So, it is a positive kind of a graph, but also deviate because of the density. See, there are 3 densities, one is less than 12,000 kg per meter cube, and some other are the 18,000 to 24,000, which is kind of a concrete or so. So, central line you may say it is a brick, the other line maybe it is kind of a perforated things or so. So, there is a variation in the time lag. Similarly, we can also see the discriminant factor and the wall thickness, that variation, but it is reverse. If the thickness increases, the discriminant factor decreases. It is a negative kind of a graph, but it is not mostly a straight line graph, it is a kind of a the non-linear kind of a graph, but it's the impact is negative, increase of the thickness, impact is negative, or impact is going to be reduced. So, that means, if the thickness is high, the wall can store more heat. So, it will not going to pass the heat so much of energy to the inside the room. So, that is why the inside room temperature will not going to shoot up and go close to the outdoor temperature. So, there will be a considerable amount of the mean peak temperature difference between the outdoor and the indoor, and that is why the discriminant factor is less. And in this particular right hand side graph, there are 3 lines again. So, if it is insulated, suppose the same wall, same thickness wall, suppose if I take the 2000 thickness wall. So, for the if I take this 3 point, because this 3 point lie on the 200 mm thickness. So, what happened? If what is the first lower one? Lower one is the external insulation. If I give the insulation externally, it will be better. It will be better that the discriminant factor is 0.2. But if I give the internal insulation, then it come about 0.3 or something, little more than 0.3 or so internal insulation. So, it is always better to give the external insulation. If I want to give an external insulation, so it is same thickness, same material can be provided in the externally. So, initially it can going to stop the heat propagation or the heat conduction. Internally, for still better, but the discriminant factor will be little bit high. But if you uninsulated cases, maybe if I am not interested for any insulation or so, it has its own discriminant factor, which will be maybe 0.45 or something like that. So, that means, if I have a choice that should I insulate a roof on the top surface exposed to the outside top surface, or should I go for the bottom surface. So, it is always better to go for the top surfaces also. So, next is we will see the time thermal time constant calculation. So, this is one of the parameter which was devised, and it was given in the SP 41, our Bureau of Indian Standard Code. It is the ratio between the heat stored Q divided by the U factor, the U value, and it is actually governed with this equation, where the L is the thickness, K is the thermal conductivity, the rho is the density of the material, C is the specific heat of the material, and F naught is the outdoor or outside the surface conductivity. So, if this particular equation holds good when it is a single leaf or it is a homogeneous wall. So, no plastering, nothing, just a brick wall or maybe a concrete wall, shear wall kind of a thing external. So, here if I see this particular L is going to be E in your meter. See, I am just first computing this product of this L, rho and C. So, if I say that the L, rho and C, the unit will be in meter, and this is the density is kg per meter cube, specific heat is your joule per kg degree C. So, that means this kg and this kg gets cancelled, this is going to be meter square. So, this is joule per meter square degree centigrade, whereas this bracketed terms will be maybe it is of L by K. So, L by K is also going to be same as L by F naught, which will be, this is meter and this is watt per meter degree C, this value of the K, this is the K value I am taking and this is the L value. So, this is going to be my meter square degree centigrade watt. So, if I now multiply these two, this one and this one, this two if I multiply. So, this is joule per meter square degree centigrade multiplied by meter square degree centigrade by watt. So, this cancels, watt is nothing but joule per second. So, these joules cancels and second goes up. So, it is in second. So, it is a time unit. So, how much time it can store some kind of the heat, something like that, it can give you a kind of idea. So, if I have series of surfaces, so practically we have this kind of a scenarios, series of surfaces, then we can actually use this equation a little bit modified from the, this is the first layer, outside layer, first layer. So, that means this is the L1 layer. So, all are L1. This is the second layer equation and this is the third layer. So, like that I can go for fourth layer also, third layer equation. Only the change is that the last part in the bracketed term is by 1 by 2. So, half of the term and rest all are the same, the will be the same. So, we will see one part, and these are the values that I have taken from the book and I will see some of the cases. So, suppose there is a brickwork of 190 mm brickwork having some 10 mm plaster both the side. So, I have noted down the L, K, rho and C values for the plaster and I calculated the L rho C and L by K values of that, and similarly I have found out the big values, you see the thickness changes, the K value changes, all these things are changes, and this is the values for the L rho C and all. So, then I have computed this. So, in the first case this 0.05 is nothing but the 1 upon F naught. So, that is constant for all the bracketed terms. So, these are that value, and first one is the 0.5 times this L by K, second case it is 0.5 times this L by K, and third case 0.5 times by L by K, and the second term there is a L1 by K1 and the third term there is L1 by K1 and L2 by K2. So, this is actually L3 by K3 by 2 sorry, and this is L2 by K2, this is L1 by K1, and these are the 3 multiplication of what I am getting from the earlier slides. This is 13843 and 13843 and 304 are directly taken in this poetic, 304 in the central case and 13843 for the terminating 2 case. And then I found out that calculated and computed 16.6 hours is the thermal time constant, right. So, similarly, I have discussed few more. So, 250 brick wall I have calculated, I found it is 19.5, it is a homogeneous case. So, I have used the first equation and I have taken some other values of the last problem, I have taken some other values of this coefficient or this parameter, because there may be some changes for the different type of brick may give you different type of different values of density or those thermal constant or so. So, here if I take a smaller thickness, half thick, I have to see what is going to be the change. I will be definitely logically say that the thermal time constant will be less than 19.5 hours, and I have computed. Only change is the thickness L value, rest all the rho and C will be the same, because that is same material, and I got 6 hours. and it is so, the thin wall will never going to protect that much, the thick wall will going to protect that much. Half of the thickness almost increase 3 times, more than 3 times the thermal lag or whatever. But it is not the thermal lag, it is the thermal the time constant that is going to be storing the heat and sending the heat, how much U value versus this storing the heat. So, I have computed for 125 mm thickness concrete wall. So, value is 7.11 hours. Even I have computed for a 6 mm glass. Can you guess how much will be this? It will be very, very less, because it is 6 mm only, and yes, it is less, it is only 10.8 minute is the thermal constant, thermal the time constant. It can actually store, and that divided by U is almost about 10.11 minute or so, right. So, you see this, it depends upon lot of things, mostly it is thickness and mostly it is depend upon the density and the specific heat. So, now let us see another very interesting case. So, in the first case I have kept the outside concrete 75 mm and inside 250 brickwork. So, in this case the concrete values are like this, L rho C and the L by K, and the brick values are like this, and if I now compute, I got 27.42 hours, very high value. But let us see is this particular thermal time constant, what will be the change if I just change the orientation. So, if I just put the concrete inside and the brick outside, it may sometimes look like it will be the same, it is not, it will be some difference will be there. The earlier one, it was 27 hours, and this same calculation if I do with that, the change in the 2 by L by K values or so, I found it is 37.97 hours, much higher values in that case. So, if I put the concrete inside and the brick outside, something like that. So, this is the scenario. Now, let us see in the final that the periodic heat flow estimation. So, in that estimation there are 2 components. One component is the average heat flow through a full cycle. So, full cycle is the temperature changes from the morning to evening or evening to night. So, if I take the mean temperature, so from that mean temperature I found out what is the deviation. So, basically this we did in the last couple of lecture back in case of the CDD method or so, and I found that particular deviation from the mean temperature of the overall 24 hours with the indoor set point temperature, and then I multiply with the A and the U values of the thermal envelope or the building envelope. So, that is one of the steady state scenario. Why steady state scenario? So, I am assuming that a mean and playing with the indoor set point temperature, where indoor set point temperature Ti is going to be constant, or I will keep that constant for the controlled environment or so. So, that is what is a steady state for all the 24 hours is the same way I am assuming it is flowing, but there is a second component also. In the second component I have using the 2 things, one is the thermal lag, and I have there is little typological error, there should be a mu in it, I will correct it and send it to you. So, there is a thermal lag of some 5 hours and there is a discriminant factor of mu. So, that has to be taken into account, and then this T phi is nothing but your, if I go to, and now this two Q1 and Q2 has to be added, and this is a time dependent calculation. So, after T phi hours, after 5 hours the temperature is supposed T phi, and that T phi is the sole air temperature of the outdoor surface, and how much is deviated from the mean, that I have to compute. So, the first part and the second part is now added together and to compute, and that will going to compute my total heat gain through the envelope by virtue of the diurnal or maybe a kind of a change of temperature. So, A and U, you know what is those Tm is the mean temperature. So, I have to take all the outdoor temperature for 24 hours and calculate the mean. Ti is the set point temperature indoor, that is the constant. T phi is the outdoor solar air temperature after 5 hours. The phi, what is phi? Time lag. Suppose the material is having 2 hours or 3 hours of phi. So, I have to take for 2 o'clock the earlier 2 hour or 3 hour earlier the solar air temperature. So, that is the T phi. I have to calculate for each hours and I have to segregate that one after how many hours or so. Mu is the discriminant factor, phi is the time lag. So, suppose this is the a series data, so time series data of temperature from 12 to 12, and I am interested to compute, and these are the values I have given. I have given 10 meter square of the area, 3.5 is the u value, and daily mean temperature. So, the mean temperature of this I have computed T mean is computed as 24 degree centigrade, and the indoor temperature I kept as 20 degree. I have assumed that that material has a 0.4 discriminant factor and the 3 hours of time lag. So, that I want to I am interested to find out the what will be the heat flow at 14 hours at 2 o'clock in the afternoon. So, I have to put everything over here in this equation. So, I have to go back, I have to go back 3 hours and I have to note down what will be the TSA at that particular 3 hours back from this particular point. You have to go back. So, that is 32.5 degrees. So, that will be my T phi, and then I have to put everything. So, 10 is the area, 3.5 is my u value. What is 24 and 20? This is the T mean temperature from all the data 24. Indoor set point temperature I have kept as 20 degree. 0.4 is the mu, that is your discriminant factor, and 32.3 this is the time lag solar air temperature 3 hours below, because I have assumed that my material is giving me a 3 hours time lag. So, it is 32. So, I am not taking the exact 39 for this, I am taking 3 hours back and finding out the solar air temperature of that 3 hours back, 32.3 minus 24 is my. So, this is my T phi I should say at behind. So, it will be around 11 hours, and this is again T mean. So, that gives me this is already I have written over here. So, by computation I got 256 watt. By this computation I got 256 watt. So, that much heat will be actually propagated at the time of 14 hours or so. That means, the first part of the equation, the A into U into T m and T minus T I is the steady state overall period of my the temperature variations also. The second part is the lag stage or with the discriminant factor also, that changes every hour. It is going to change, because every hour next if you go to the 15 hours you have to take the 3 hours earlier solar air temperature, like that. So, I have again, suppose I have computed for this particular thing, and suppose I have computed for 17 hours same. So, 17 hours if I see, that means evening afternoon 5 o'clock. So, I have to go 3 hours back and I have to take the 2 o'clock the solar air temperature, which is 39 degree. So, just like that, the 3 hours phase lag temperature I have to take, I have to put it over there. Only change will be in this particular equation will be, instead of 32 point something was there 32.3, instead of that here only change will be in this 39, and the heat gain is 350 watt, which was 256 over there. So, more heat will be conducted at 5 o'clock with respect to 2 o'clock, but probably yes, the solar air temperature at 2 o'clock is much higher than the 5 o'clock, because it is the effect of 3 hours behind that heat will be conducted through the wall or something like that. So, it is it is going to be depend upon the point this mu factor. If it is mu factor is low, so this second part will be low, and if there is a high amount of T phi, so it will be the peak will be shifted much more. So, we will see. So, I have computed this for same values whatever we have just now seen, and with this now we have I have computed for 6 hours. 0.4 is the discriminant factor, and all our 10 meter square is the area, 3.5 is the u value, T mean is 24.125 degree, and all those indoor temperature is kept at 20 degree. So, this is the variation. What is the variation? The blue line indicate the outdoor temperature. So, that is in the TO in this axis, and this in this axis is the Q. So, that is in watt, right. So, you see there is a shift, the highest peak temperature is at 15 solar air temperature, but there is a shift of 1, 2, 3, 4, 5 hours almost, and the peak is also going to be over there or 350 or something like that. So, I did it for 2 combinations. One combination is the last combinations, which is 0.4 is the DF, which is purple color curve, and 6 hours is the TL, the time lag, and second one, which is a this dark green color, where I have used a DF of 0.8. So, it is a thinner material, maybe 0.8 and 3 hours of time lag. So, if you use that, so see the purple color has much more damping, the same wall, same U value, same A. So, there is a much more damping. It was almost the highest one is almost like 350 or something, here it is 600. Okay. There is a time lag is also small, because it is 3 hours, and this is high. So, like that we can compute. So, what we seen over here is we studied or discussed the thermal time lag constant, which actually shows the heat capacity versus the U value of the material, and also we have computed or discussed the periodic heat gain through a wall element or any element due to the time lag and the discriminant factor. Thank you very much.